Okay? And we're not really referring just yet to our free body diagram, but let's just get down everything we have. Okay? So we know we've got a tension force, we know we've got a gravitational force, and we're going to pick out our other variables. Okay? It says that the rope can withstand a maximum of 525 newtons worth of force. Okay? So that's our maximum tension force. So we're going to kind of use that to basically to compare. Okay, is our acceleration going to put that rope in danger of breaking or not? Okay. It says it's being lifted 3 meters, so that's our distance final. It's moving finally at 3 meters per second. Okay, and what's our initial velocity? 0. Okay, so do we have a kinematics equation that will allow us to solve for the acceleration of our object? Yes, we do. Okay, so let's go ahead and do that first.
So we, on this equation, we can use our kinematics equation?
I'll probably put them up on the board if we need. So let's think about why in the first place do we have to solve for acceleration? Okay, we'll get to that point in a second, but let's go ahead and solve for it, and then I'll show you why we have to do that. Do you know what it is?
No, I just have a quick question for that equation. Are you going to pick up?
We need to solve for acceleration. Which of our kinematics equations can we use to solve for the acceleration here?
2. Yeah, you're right.
The third, right? We don't have time here. So you need to have your kinematics equation out. Okay, get those out so we can see them. We need to use the equation that looks like this. VF squared equals VI squared plus 2A dF minus DI. Okay, because we don't have time. We don't know how long it takes it to make this transition. So our final velocity is 3. Initial velocity is 0. 2. We're solving for A. Distance final is also 3 meters. Okay, so we've got 9 equals 6A. That means A is equal to about 1.3. Is that right? Okay. So that's meters per second squared. Okay, that's the acceleration of our object. Is it accelerating in the positive direction or the negative direction? My bad. 1.5. Okay, sorry. So is our object accelerating in the positive direction or the negative direction? The positive. And how do we know that? Yeah, because our acceleration is positive, which means it must be moving in the positive direction. Okay? So if I go back to look at my free body diagram, which of these forces should be larger? The tension force, right? So I'm going to shorten my gravitational force here a little bit. Okay? So essentially, they're picking it upward, but they're accelerating in the positive direction. Okay, so we've got our acceleration. We've got a few other things. I'm going to get rid of our kinematics here because we solved that already. Okay? Now let's take a look at, we need to determine if this rope is going to be able to hold. Okay, so that means we need to solve for the tension force, and then we'll compare it to the maximum amount that it can withstand. Does that make sense?
Yeah.
Okay, so let's set up our net force equation. F net. What is the net force always equal to? Mass times acceleration. Okay, that's one way that you can solve for the net force. What's the other way that we can solve for the net force? Do you remember? Kind of, okay, F1 minus F2. What do we know about the net of anything? What's that mean? The sum or the overall. Okay, so when we say net, we're going to take our positive forces minus our negative forces. Okay, so right when we take upward forces minus down or rightward minus leftward. Do you remember that part of it? Okay, so what's our upward force here? Tension. And what's our downward force? Gravity. Okay, so our goal here is to basically look at our tension force and compare it to the maximum amount that that tension or that rope can withstand. If we know that the net force is equal to mass times acceleration, and we know the net force is equal to tension minus gravity, can't we do a substitution there? Okay, so we're going to take mass times acceleration equals tension minus gravity. Okay, and that's the force due to gravity. Now we can start looking at some numbers here. Okay, so I'm going to move this over here. We know our mass is equal to 50 kilograms. Our acceleration we solved to be 1.5. Okay, we don't know our tension force. We're going to solve for our tension force, then compare it to here to answer the final question. Okay, so we're solving for our tension. What is Fg always equal to? Fg is always equal to
9.8.
no, mass times 9.8. Remember the weight. This is weight right here. Weight is always equal to mass times 9.8. So we need to take mass times 9.8. And we don't need to use negative 9.8 because the negative is taken care of when we subtract out the downward forces. So the negative is taken care of here. Okay, as long as you do upward forces minus downward, you're going to be able to take care of that negative. So let's do the math that goes with this. 50 times 1.5 is 75. Ft minus, what is this, about 490? Okay, 490. So now to solve for the tension force, we're going to add that to the other side. Equals 565 newtons. So if this object accelerates at this rate, this is how much tension is going to be exerted on that rope. Is it going to last or is it going to break? It's going to break.
I have a question.
Yeah.
On the
Okay, so essentially you can abbreviate this to say the max tension of this rope is 450 newtons. We want to fill the bucket to this mass, and we want to find out how fast we can accelerate that bucket without having it break, without having the rope break. We want to find the max acceleration, so that means we're going to use the maximum tension that it can withstand. Does that make sense? All right, let's start with our free body diagram again. Okay, Caleb, can you give me one of the forces here of our free body diagram? Tension, good. And is it going up or down? Up, good. And Candace, can you give me the other force? Gravity, good. And should gravity be greater than, less than, or equal to our tension force, do you think? You don't know yet. Okay, that's fine. Good. We don't quite know yet. We can guess, since we want to accelerate it up, we can probably guess that it's going to be less than. Drawing it to scale at that point is not super important, just as long as you have those forces listed. Okay? So now let's start with our F net equation. F net, when I say F net equation, that means I want you to start looking at positive forces minus negative forces. So what's our only positive force here? Tension. And what's our downward force, or our negative force? Gravity. Okay, could everyone get to this point by themselves? Okay, I hope so. That's where you should be. Okay, we want to make sure that everyone is getting to this point by themselves, including the free body diagram. Now we can start plugging in some substitutions here. What can we always substitute for F net? Good, mass times acceleration. We know that our force of tension, our maximum tension here is 450. We know that the mg is mass times 9.8. Okay, what are we solving for here? What's our goal? Acceleration, good. What is the greatest acceleration? So we can take 42a equals 450 minus 42 times 9.8. And we're going to end up solving for a. Make sure you have a calculator out plugging this in.
So on the FG, it's the same thing as the other side, so it's MA as well.
No, always for FG it's mass times 9.8. Always.
Okay, so that's
So you're going to have two different accelerations. One is always gravity, one is the acceleration of the whole system.
okay.
Okay? If FG is always,
Times gravity.
yes, m times 9.8. Always. That's why I heard rumblings. 0.91, is that, we agree? Okay, good. So we're going to look at 3 situations that's happening in the normal force. The first of which is just sitting at rest. So I'm going to draw it a little bit more clear. Normal force, gravitational force. Okay? So let's take a look at this. I want you to keep this in your mind as we're going here. Let's say the box has a mass of 40 kilograms. That's what we're going to say. Okay, our box has a mass of 40 kilograms. For the first situation, we want to find the normal force. We want to find the normal force for all of these situations. But for this one, it's sitting at rest. Okay, there's nothing else that's touching it. So if we want to find the normal force, we're going to set up our net force equation. What is our positive forces here? Normal, good. And what's our gravitational force? Good. Okay, so here's where it gets tricky. We know that we're going to substitute mass times acceleration minus mass times gravity, right? Okay, we know that we can do those substitutions. What's the acceleration of this box? 0. It's not moving, right? The box is at rest. Even if it was moving at constant speed, our acceleration would be 0. Okay, so when our box is at rest like this and it's not accelerating vertically, our net force is equal to 0. Okay, so we're going to take normal force minus mass times gravity. Okay, and that's what, 380 something, 390 something? I don't know. 40 times 9.8.
It's 392.
392. So that means that our 0 equals normal force minus 392. So to solve for the normal force, we're going to add it to the other side. So our normal force for the first situation is 392 newtons. Okay? Think about it this way. When our object is not accelerating in the vertical direction and when there's no other forces acting on it, our upward force should equal our downward force. Okay? Which is exactly what we did here. Okay? On the bottom. Our upward force equals our downward force. Okay? So as long as there's no other vertical forces acting and it's not moving in the vertical direction, you know your normal force would be equal to your gravitational force. Okay, for this object that's nothing else is happening to it. It's just existing vertically, kind of. Okay? Let's look at the second situation. Okay, so this one was 392. Our second situation, what's happening with this one? We're lifting it, right? He's attempting to lift it. It's not getting off of the table yet, so he's applying an upward force, but it's not leaving the table, so it still does have a normal force, okay? What would happen if I lift it off of the table? What would be the normal force? Yeah, what would be the normal force if I lifted it off the table? 0. If it's not touching the surface, it doesn't have a normal force. Can I have a negative normal force? No, I cannot. Okay, I cannot have a negative normal force. Okay, so our free body diagram here looks a little different. We've got gravity, we've got a normal force, and we've got a applied force. Okay, and we can add them right on top of each other, just like that. Okay, 2 vertical forces this time. So for our second situation, we're going to set up F net equals our upward forces minus our downward. So what are our upward forces? Applied. It doesn't matter which order you add them in, but yeah. Normal force plus applied force minus gravitational force. These are both upward. This is downward. Okay. What's the net force of our system here? MA, good. But for this example, what is it? It's 0, good. Okay, so our force applied we know is 50. That's what it says right up here. We're lifting with 50 newtons. We're trying to solve for our normal force. And we know the gravitational force of our object was 392. And since our mass didn't change, we already know it's 392 because that's mass times 9.8. Okay? So we're going to say 0 equals 50 minus 392 plus Fn. Okay, I just rearranged there, but all you need to do is combine that. I just didn't do it in my head. Okay? So we move this to the other side, which means our normal force here is 342 newtons. Okay, greater than or less than when our object was just at rest? Less than, right? Because we are lifting it up. We're taking some of that pressure off the normal force. Okay, so as you attempt to lift something, you're basically relieving that normal force a little bit. So that's why our normal force is less than in this example. Did you have a question, Wyatt? Down on the box. So do you think our normal force is going to increase or decrease? It's probably going to increase, right? Okay, so let's see it. Our free body diagram here. We've got a gravitational force. What other force do we have going in the downward direction? Yeah, our applied or our push or whatever you want to call it. Okay, and then our normal force is in the upward direction. So now we're going to set up our F net, and it's going to equal our upward force, which is? What's our upward force?
Fn.
Normal. And what are our downward forces? Good. So you need to pay attention to your applied force. It doesn't necessarily always mean your applied force is in the positive direction. Your applied force could be in the negative direction if you're pushing. Okay? So is it accelerating vertically?
No.
No. So what do we know our net force is equal to?
0.
0. Good. Okay. Normal minus 50 minus 392. Okay, so we got 442 newtons. So I'm going to show you how we solve this, because this is obviously something you do in real life all the time. Okay? Stand on a scale in an elevator. Okay? But essentially what we're looking at here is it's going to show you a different weight because you as a whole are accelerating. You're not just standing still on a scale. So you're going to read a different weight. So let's look at what this means. Okay, 10-kilogram dog stands on a scale in an elevator that's accelerating downward at 2 meters per second. What will the scale read? Okay, which is essentially the normal force. When we look at physics problems with scales, that means we're really essentially trying to find its force due to gravity. You're trying to find really its weight or its reading of the scale, which is in newtons, not in kilograms. Okay? So when we try to find these scale readings, this is what our free body diagram is going to look like. Okay? Here's my little dog. Gravity's pulling down on him. He's standing on the scale, which is exerting a force back up onto him called what?
Fn.
The normal force. This normal force that the scale is exerting is what the scale will read. So that is what you should solve for on these elevator problems. Okay? When you stand on a scale, also called the normal force, so that's what we're going to try to solve for here. Okay? Yeah.
10 kilograms doesn't matter.
It will when we look into our, because what's our overall goal here?
To find Fn.
Find the normal force. So let's set up our F net equals what minus what?
Fn minus Fg.
Good, Fn minus Fg. So now we can do our substitutions. Mass times acceleration equals the normal force minus mass times gravity. Okay? Our mass is equal to, our acceleration is equal to, what's our acceleration of our elevator? -2. Very good. -2. That is extremely important. As you're going downward in an elevator, you're taking some pressure off. Yeah, you're going to seem like you weigh less. Okay, if you go up, then you're going to look like you weigh more. Okay, so as we go downward, it's going to appear as though this guy weighs less. Okay, so we got -20. So we gotta move that to the other side, which means our normal force is 78 newtons, not kilograms, newtons. Okay, so at rest, this dog would have looked like he weighed 98 newtons. When he's accelerating downward in an elevator, it looks like he weighs 78 newtons. A 2-kilogram bowling ball is sitting on a table. If someone exerts a 12-newton force in an attempt to lift the ball, that means they're not getting it off the table. What's the normal force going to be? Okay, so they're not actually getting it off the table, but they're trying. Okay, let's set this one up. I want to see your free body diagram. I want to see your net force equation. I want to see you working here. This is back to some horizontal stuff. So you need to draw the free body diagram. We want to find this one, the mass of the box. Okay, so let's go ahead and get your free body diagram going. Let's get some practice with that net force. But we're back to horizontal now. Yeah, you could put it a -0 or you can just leave it. Either way. Either way is completely fine. Putting that -0 just kind of tells you, like, okay, I checked and there's no leftward forces. So you can put it in there or you can leave it. It doesn't matter. But we're going to take mass times acceleration, which we know acceleration is 5, equals our 30 newtons, which means our mass is 6 kilograms. Very good. Very good. I want to see how far we can go, kind of rolling on our own here. Okay, I think you can do this one on your own as well. Okay, so as we set up our free body diagram here, applied, friction, normal, gravitational, okay? Our F net in the horizontal direction, is equal to force applied, minus force of friction. On the other side of that, when we're looking at our normal force, we're going to say F net in the vertical direction. So you can put a little Y there if you want to, and put a little X for that horizontal one. If you want to keep them separate, that's fine. Should be our normal force minus gravitational force. This right here, listen, this normal force and gravitational force equation, you need to pay attention to if this object is accelerating in the vertical direction. And in this case, it was not, right? It was just resting on the table. It wasn't accelerating vertically. It was only moving horizontally. So this is 0, okay? And when that F net is 0 in the vertical direction, that means your upward forces have to equal your downward, okay? All right, very good.